Cameron Maud was an ordinary 3-year-old girl from North Carolina who loved playing with dolls and drawing. However, her life changed abruptly when she began having unusual seizures, falling, and twitching uncontrollably. Doctors diagnosed her with Rasmussen's encephalitis, a rare disease that inflames the brain and causes frequent seizures. Over time, Cameron's condition worsened. She stopped speaking, could not attend kindergarten, or play with other children. Having seen this, the doctors offered the parents a choice. Either the situation would continue to worsen, or they could try to carry out a complicated and extremely risky operation to remove the right half of the brain. Despite their hesitation, her parents decided to go ahead with the surgery. After the 12-hour surgery, Cameron was unable to move her left arm and leg, but the doctors and parents persevered and continued to work with her every day. Miraculously, after a month, Cameron began walking again and quickly regained the ability to speak and smile. She restated her dream of becoming a ballerina, and that dream was now within her reach. Cameron is now a teenager. She is doing well in school, especially in math, and although she has a slight limp on her left leg, it does not prevent her from dancing or playing sports. This remarkable recovery is attributed to neuroplasticity, the brain's ability to reorganize itself. The left hemisphere of Cameron's brain adapted to take over the functions of the remote right hemisphere. Unlike a computer, the brain is a dynamic, living system that can change itself. Although neuroplasticity declines with age, it is still impressive in allowing our brains to adapt and grow with new learning experiences. The concept of neuroplasticity has also paved the way for advances in technology and biology. In early 2024, Neuralink successfully implanted its first chip into a human brain. This technology allowed paralyzed Noland Arbaugh to control a computer cursor by simply thinking about its movement. One day I fell asleep while using it, and the cursor moved while I was asleep and was still clicking. I fell asleep for about 5 minutes, and when I woke up, there were about 10 different applications open on the computer. Arbaugh is able to use the chip almost every day from morning to night. Sometimes my day starts at 7 a.m., and I use the implant until 11 p.m. This isn't the stuff of science fiction. It's a reality currently in the testing phase. The neurochip, designed by Neuralink, is a small receiver capsule worn behind the ear like a hearing aid, connected to the brain by filamentous electrodes that are 4 times thinner than a human hair. With this chip, Noland Arbaugh can control a cursor on a computer screen just by thinking. He uses the technology to send social media messages, respond to emails, read comic books, and even book hotel rooms. He's also using it to learn Japanese. Neuralink's efforts are not limited to cursor control. The company aims to restore vision for the blind and stimulate muscle movement in paralyzed individuals. Neuralink's ambitions go even further. The company's long-term vision is to create a symbiotic relationship with artificial intelligence. Founder Elon Musk believes that a direct brain-computer connection will help people keep pace with AI advancements. At the core of modern neurotechnology is the brain, a complex, nearly 1.5 kilogram organ, one of the most intricate objects known to science. As neuroengineer Tim Hansen says, the brain is one of the most information-dense, structural, and self-organized substances known. And we're not just talking about the brains of famous scientists like Einstein or Marie Curie. Every human brain is amazing. For example, your brain is made up of about 170 billion neurons and glial cells. Each of these cells acts like a small city containing the complete set of our genes, constantly exchanging signals and forming a myriad of connections. The complexity of this neural network is so great that new branches of mathematics are required to describe it. There are as many connections in 1 cubic centimeter of your brain as there are stars in our galaxy. This small organ is more complex than anything we can comprehend. Even if you don't consider yourself exceptionally intelligent, remember that you are the most active and intelligent being on Earth simply because you are human. Humanity has come a long way, and we are unique in our quest to understand our own cognitive code. It's like having a computer study itself. Let's explore how the brain creates our reality, how it stores memories, adapts to new information, formulates thoughts, and how it all relates to neuroplasticity. This video is based on the book, The Brain, The Story of You by neuroscientist and Stanford University lecturer David Eagleman, as well as a few other books I'll mention later. If you appreciate what I do and want to support my work, please like, comment, and subscribe. Unlike many animals that are born ready to live, such as a fawn that is on its feet in minutes or a duckling that can swim immediately, a human baby is born completely helpless. In fact, this helplessness is an advantage. Humans are born before their brains are fully formed because our brains are too big to pass through the birth canal when fully mature. Evolution has found a workaround. Most of our brain development happens after birth. At birth, a baby's brain is not fully ready. Neurons are present, but have not yet made connections. To learn to communicate, neurons form connections known as synapses, which act as bridges between neurons, transmitting signals. In the first 2 years of life, synapse formation is extremely rapid, up to 2 million new connections every second. By the age of 2, a child has twice as many synapses as an adult. After that, the pruning process begins, in which about half of the synapses are removed, leaving only the most frequently used connections. This pruning process helps shape who you will become in adulthood, not by adding new structures, but by refining and removing unnecessary ones. In 2000, scientists conducted an experiment with newborn kittens. They divided them into 2 groups. One group grew up in a room with vertical stripes on the walls, and the other group grew up in a room with horizontal stripes on the walls. After a few months, the kittens grew older and were released into the wild. And then something amazing happened. The kittens from the room with the vertical stripes recognized vertical objects like poles and trees perfectly, but tripped over horizontal obstacles like thresholds and steps. Conversely, kittens raised in a room with horizontal stripes easily navigated steps, but had difficulty with vertical objects such as poles. This experiment showed that the kittens' brains learned to see only those lines in their rooms. It developed many connections for recognizing these lines, while connections for other lines did not develop. What does this reveal? It shows that children's brains are like construction kits. During the early years of life, we build a foundational understanding of the world. If only certain types of experiences are available, the brain will develop connections based on those experiences. For instance, if only red blocks are available, we can't build a rainbow. We need blocks of various colors and shapes. If only one type of experience is provided, the brain's development will be limited to those specific experiences. A striking example of this principle comes from a large-scale social experiment conducted in Romania in 1966. President Ceausescu, aiming to boost the population, implemented harsh measures including banning contraception and abortion, and imposing taxes on small families. This led to a dramatic increase in birth rates and subsequently overcrowded orphanages. By the time Ceausescu was ousted in 1989, these orphanages housed 170,000 children. Dr. Charles Nelson, upon visiting these institutions, was deeply alarmed by the conditions and their impact on the children's development. Children were placed in rows on plastic pots and given the same haircuts regardless of gender. The children were dressed the same and fed on a schedule. Everything was done mechanically. Babies quickly learned not to cry because they were not responded to. Children were not picked up or played with. Although basic needs were met, babies were fed, bathed, clothed. Infants were deprived of love, care, support, and any stimulation. Nelson conducted a study and found that the infants' IQ scores ranged from 60 to 70, well below the average score of 100. By studying the electrical activity of these children's brains, Nelson found extremely low neuronal activity. Child's brain is like a sponge. It greedily absorbs everything around it. Smiles, words, touch. If you keep a sponge in an empty room, it stays dry. So is the brain. Without emotions and new knowledge, it cannot grow healthy. Fortunately, there was one piece of good news after all. Nelson discovered that the brain can regenerate. The earlier a child is placed with a loving family, the better the outcome. Children return to families before the age of 2 tend to catch up quickly with their peers. After the age of 2, improvement is also possible, but progress depends on the age at which the child was taken from the shelter and the degree of developmental delay. Let's conduct a little experiment. Close your eyes and think back to your last birthday. Picture where you were, who was around you, and the smells and sounds you experienced. You might not realize it, but you've just traveled back in time, all thanks to your brain's remarkable ability, memory. The hippocampus, named after the Greek word for seahorse due to its shape, plays a crucial role in forming new memories. It acts as a kind of drawing board for memory. When rats learn to navigate a maze, their hippocampus encodes the memories of different sections of the maze. Each part of the maze is stored in a specific area of the hippocampus. However, if the rat is given a new task and returns to the maze after a year, it will struggle to remember it, as the hippocampus will have cleared space for new memories. This is similar to the plot of the film Memento by Christopher Nolan, where the protagonist uses tattoos as a form of memory due to a condition called anterograde amnesia, caused by damage to the hippocampus. Alzheimer's disease also starts in the hippocampus, with memory issues being one of the first signs before the disease spreads to other brain areas. In 2000, Eleanor Maguire, a neurobiology professor at University College London, studied the brains of London cab drivers. To become a cab driver in London, one must pass a challenging exam known as the Knowledge, which requires memorizing an extensive number of streets, routes, and landmarks. And it's a non-trivial task at all. 320 different routes around the city, 25,000 individual streets, and 20,000 landmarks and places where a passenger might want to go. Hotels, theaters, restaurants, embassies, police stations, stadiums, and so on. It takes an average of 3 to 4 years to prepare. Maguire scanned the brains of cab drivers before and after training and found that those who passed the exam had a marked increase in the size of the posterior hippocampus. This change demonstrates neuroplasticity, the brain's ability to adapt and grow in response to experience. Even Albert Einstein's brain demonstrated neuroplasticity. Research showed that the area associated with the fingers of his left hand was enlarged, forming a fold in the shape of the Greek letter omega. This was probably a consequence of Einstein practicing the violin extensively. Similarly, pianists have similar folds in both hemispheres of the brain. We are constantly evolving, and our cells renew themselves, making us physically new every 7 years. But what defines our essence? It's our memory, although it's more complex than it seems. When you recall an event, such as a friend's wedding, your brain creates a unique map of that memory, including details such as laughter, the flavor of tea, and specific moments such as a loud hiccup during a toast. Over time, this vivid memory fades, and while you remember the general atmosphere, specific details slip away. For example, you may remember the groom's parents crying, but forget what they were wearing or who was sitting at your table. The brain doesn't store memories like a videotape. Instead, when neurons form new memories, they can blur and alter the original memories. Subsequent experiences can also change how we remember past events. Let's say the couple divorced 5 years later. Now, when you think back to the wedding, you can see signs of a future breakup. Do you remember them arguing emotionally about something several times, or that there were awkward pauses between them? Your brain is involuntarily rewriting your memories, adjusting it to fit the new information. Best of all, you may not even realize these changes. You will absolutely remember everything as vividly as the day of the event. The enemy of memory is not time, but other memories. Each new event requires the formation of new connections among a finite number of neurons. Professor Elizabeth Loftus at the University of California decided to test how malleable our memory is. She found volunteers who were shown videos of car crashes and then asked several questions. The gist of the experiment was different wording. When I asked how fast the cars were traveling before they collided or how fast the cars were traveling when they crashed into each other, the speed estimates varied. The subjects thought the cars were moving faster when I used the verb crashed. Loftus' next experiment was even larger in scope. She decided to test whether people could remember things that never happened. She invited volunteers and secretly contacted their families, collecting real stories from the participants' childhoods. She then created a set of 4 stories for each subject. 3 of them were authentic, taken from relative stories, but the 4th was completely made up. This fictional story was very believable. It told how a participant in the experiment, as a child, got lost in a shopping mall. Then a kind elderly woman found him and helped him find his parents. This story, however, could have happened to any child. In the interview, Loftus told the participants all 4 stories without revealing which one was false. And that's where the surprising thing happened. At least a quarter of people said they remembered the fictional incident at the mall. And participants weren't just agreeing that the event had happened. They began to recall details. They may have talked to the elderly woman who rescued them. Over time, the false memories grew more and more detailed. The old lady had a ridiculous hat. I was holding my favorite toy. Mom was so excited. And how much can we trust our memories? And how does it affect our understanding of our own selves and our past? Look around you. What if I told you that everything you see is just an illusion created by your brain? It might sound like a wild exaggeration, but let me explain. Beyond our conscious experience, reality appears very different. There are no colors, smells, or sounds in the raw data we receive. Our ears convert variations in air pressure into electrical signals, allowing us to hear. Our noses detect molecules in the air, which our brains interpret as different smells. This is how our sensory systems work. Our brains, shaped by millions of years of evolution, transform this raw data into the vivid experience of the world around us. Take a look at this chessboard. You see 2 squares, A and B, that appear to be different colors. However, they are actually the same color. You can verify this by covering the rest of the image. Why do the squares look different despite being identical? This illustrates that what we see isn't necessarily what is. Our brains don't merely receive sensory information. They actively interpret and construct our version of reality. The brain is constantly searching for patterns and integrating information from multiple senses. It makes quick, unconscious assumptions about what's happening around us, and we perceive the outcome as reality. Mike May lost his sight at the age of 3 due to kerosene damage to his cornea. Despite his blindness, he became a world record holder in blind ski slalom, played soccer, earned a master's degree in international affairs, and led a GPS company for the blind. At age 43, he learned about a new stem cell therapy that could potentially restore his sight. His blindness was due to corneal damage, and the therapy seemed like a promising solution. He decided to undergo the surgery, and television cameras captured the moment when the bandage was removed from his eyes. Mike described his sensations.
Holy smoke. You see a little bit? I sure can.
My eyes were flooded with light and images. Suddenly, a dam of visual information broke through. It's amazing. The new cornea transmitted and focused light perfectly. But Mike faced an unexpected problem. His brain couldn't interpret the incoming images. One day, while skiing down the mountain, he realized that he was approaching a huge object at high speed and could not avoid it. It turned out to be a shadow. When he returned home, he saw his wife and children but couldn't recognize their faces. Even a simple car ride became terrifying. He sometimes recoiled in fear, mistaking highway signs for large obstacles in the road. Despite seeing the world around him, Mike struggled to make sense of what he was seeing. He continued to use his cane and described himself as a blind man with vision. Mike's brain had adapted to a life without sight by repurposing the visual cortex to enhance his other senses. After his sight was restored, that part of his brain, which had been trained to process non-visual information, had to relearn how to interpret visual data. Difficult and slow process. It turns out that the eyes are not a video camera. It's not enough to simply remove the lens cap. Our brains perform incredible feats, one of the most important being the integration of sensory information to make sense of our environment. Synchronization plays a key role here. For instance, during a sprint race, runners appear to start almost immediately after the gunfires, but it actually takes around 0.2 seconds for their brains to process the sound and send the signal to move. Research shows that people react faster to sound than to light, because our brains process auditory information more quickly than visual information. This is why starter pistols are used in races instead of flashes of light, despite light traveling faster than sound. You may notice that when you clap your hands, sound and sight seem to synchronize. The paradox is that theoretically we should see the clap before we hear it. This is because our brain collects signals from the different senses and creates a single perception. There is a slight delay between a real-time event and its perception. This synchronization extends beyond sight and sound. Signals from different parts of the body arrive at the brain at different speeds, with information from the toes taking longer than from the nose. However, we don't notice this because our brain compensates for the delays by giving us a smooth perception of reality. Thus, we are always living a split second in the past. What we perceive as the present moment has already happened. This is the trade-off for a holistic perception of the world. Close your eyes and turn your head. Even without vision, you will still have a mental image of the world around you. If you are in your room, you know where the furniture is and what color the walls are. Your brain continues to create a sense of reality, even when you are not receiving visual information. Imagine being placed in a completely dark and quiet room, like the isolation cells at Alcatraz, where prisoners were left alone in a completely soundproof room measuring only 3 by 3 meters. In such conditions, you are alone with your own mind, and the brain's ability to create and maintain a sense of reality is put to the test. You might think that in such a situation a person would simply stop perceiving anything, but they don't. Robert Luke, one of the prisoners, spent 29 days in prison. He described the experience. The dark hole was a bad place. Some guys couldn't take it. I mean, they'd get in there and after a couple days they'd bang their head against the wall. There's no telling how you'll behave once you're in there. It's best not to try it. Paradoxically, the prisoners' minds, cut off from the outside world, did not lose their ability to perceive, but created their own reality. Luke recalled, "I remember flying a kite. It was like it was real. Only it was in my head. Try to visualize this. You are in complete darkness and silence, yet you see vivid images." Another prisoner said that he saw a spot of light that he could mentally expand to the size of a television screen and watch it. You might think that what the prisoners experienced was just a fantasy or a dream. But no, the prisoners were not asleep. Deprived of external stimuli, their brains created their own reality, which they perceived as real. This phenomenon is due to a process called internal modeling. Our brain doesn't just accept raw data from the senses, it compares it to what it expects to see. This is why Robert Luke could perceive vivid images even when his eyes were not receiving a visual cue. His brain continued to construct reality based on familiar patterns and expectations. You may not have experienced a similar situation, but you experience something similar every night in your dreams. When you sleep, your brain continues to create vivid and realistic images despite the absence of an external sensory signal. In dreams, you often believe that what is happening is real because your brain uses past experiences to create a familiar and coherent narrative. For example, when you walk down a familiar street in a dream, you will easily recognize everything around you because your brain has already mapped the place based on previous experiences. Sometimes you can observe this internal modeling in action. For example, if you look at the back of a mask, you will still perceive it as a bulging face. This is because your brain expects to see the face in a certain way. If you were to shoot a video by moving the camera like your eyes, it would be very jerky. However, your brain smooths out these movements, providing a smooth perception. Interestingly, your internal map of the world is less detailed than you think. Take a look at Elia Rapin's painting. They didn't expect, and try to memorize it in detail. You can pause the video and look at it carefully. Now try to answer a few questions. What is on the table? What is the unexpected guest holding in his hands? What color is the wallpaper? Are there candles on the table? Is there a dog in the room? Most people, including participants in Alfred Jarbus's experiments, have trouble recalling specific details of an image after a cursory glance. Jarbus found that people tend to remember only the basic elements of an image, rather than all of its details. This discrepancy creates an illusion of perceptual completeness, where people think they are seeing an image completely and clearly, when in fact they are not. This feature of the brain is also used by magicians to perform tricks and may explain why drivers sometimes fail to notice pedestrians or other cars despite looking directly at them. Key factor in this is the brain's high energy consumption, about 20% of all the calories we consume. Although the brain is only about 2% of our body weight, its neurons require a significant amount of energy to function. To conserve energy, the brain focuses on processing only the most important information. I think you've heard many times that the brain uses several times less energy than a typical light bulb. But what if we compare our brains with modern artificial intelligence? Is AI comparable to our brain in terms of energy efficiency? Many people still view AI with skepticism. While artificial intelligence systems such as large language models and chatbots are impressive, researcher Jan LeCun argues that they are unlikely to match human thinking and planning capabilities. The brain's energy efficiency and its sophisticated data processing make it a unique and powerful organ, even when compared to advanced AI technologies. Noam Chomsky, a famous linguist and intellectual, argues that AI systems such as large language models still lack true language understanding. Roboticist Rodney Brooks agrees with him, noting that LLMs are able to mimic human reactions, but cannot make those reactions meaningful and logical. Despite these criticisms, Silicon Valley is buzzing with discussions about general-purpose artificial intelligence, AGI. AGI is a hypothetical form of AI with the potential to understand, learn, and apply intelligence in all domains similar to human cognitive abilities. AGI is categorized into two types, strong and weak. Strong AGI are theorized to have genuine understanding and a complex picture of the world, similar to human intelligence. In contrast, weak AGI will remain advanced tools with limited domain-specific knowledge and no true understanding. It is believed that a strong AGI will be able to think and solve problems just like a human. But in all domains, modern AIs are adept at performing specific tasks at a high level. For example, beating world champions at chess or recognizing faces. A strong AGI will be comparable to a PhD in all sciences at the same time. And when do you think such a powerful AI is expected to emerge? Are we talking multiple years, decades, or centuries? However, predicting when such an advanced AI might emerge is quite difficult. Current predictions vary widely, with some experts suggesting that a weak AGI could emerge by 2027 and a strong one by the 2030s. The CEOs of Anthropic and DeepMind say the same. Elon Musk says the same thing. Others, such as the CEO of Baidu, predict a more cautious timeline, around 2034. If you compare the energy efficiency of the brain and AI, it is staggering. The human brain consumes about 10 watts of energy, while performing calculations at about 1 exaflop, billion operations per second. By comparison, Summit, one of the most powerful supercomputers, requires about 30 megawatts of energy. That's 3 million times more than the human brain. Despite its enormous energy consumption, Its computational performance is 5 times lower than that of the brain. This indicates that the human brain is millions of times more efficient than even the most advanced supercomputers. So how does the brain achieve such astounding efficiency? The key lies in its complex and highly optimized structure, which allows it to perform an astonishing number of operations with relatively minimal energy expenditure. It has to do with the way the brain works. The brain processes information in parallel, with billions of neurons working simultaneously. Visualizing brain activity shows that different areas of the brain are active at different times, disproving the myth that we only use 10% of the brain. Each neuron handles both memory and computation, avoiding the bottleneck that characterizes modern computer architecture, particularly the von Neumann architecture. The bottleneck arises from the separation of processing and memory. This separation requires constant data transfer between the processor and memory, which increases computation time and reduces efficiency due to the lack of parallel processing. This inefficiency is exacerbated by the large amounts of data processed by AI systems, resulting in longer memory access times and higher energy costs. In contrast, neurons in the brain communicate via highly efficient electrical impulses. The brain uses analog computation, which is more energy efficient in communicating information. Neurons are spontaneously activated, creating background activity that helps you respond to new stimuli without additional energy expenditure. In addition, during sleep, the brain optimizes its performance by pruning unnecessary connections between neurons, increasing efficiency and conserving energy. Inspired by the brain's efficiency, scientists are developing neuromorphic computing systems. This field aims to create AI that mimics the brain by integrating memory and data processing. Neuromorphic computing uses analog memristors to reproduce synaptic functions. Examples of such technology include IBM's TrueNorth chip, which contains 1 million artificial neurons and 268 million synapses while consuming only 70 milliwatts of power, and Intel's Loihi 2 chip, which is 1,000 times more efficient for certain tasks than traditional neural networks. In addition, the University of Manchester's Spinnaker 2 chip can simulate up to 10 billion neurons in real time. Despite these advances, neuromorphic computing is still far from matching the capabilities of the brain. Imagine a brightly colored poppy flower in front of you. You perceive its red petals, green leaves, and yellow core as separate colors, but these colors exist only in your imagination. In reality, only electromagnetic waves of different wavelengths exist. When these waves reflect off the flower and into your eyes, your brain processes them and creates a sense of color. This concept is akin to how a computer converts a series of ones and zeros into a visual image on a screen. Visible light is just a tiny segment of the electromagnetic spectrum. If you imagine a line stretching from the Earth to the Sun, the part representing visible light is only about 1 centimeter long. The rest of that line is filled with other types of electromagnetic waves that are invisible to us. These include radio waves, X-rays, gamma rays, and others. Our limited ability to see only this small portion of the spectrum is due to evolution. Our eyes have developed to detect the range of wavelengths most critical for our survival and reproduction. It's similar to tuning a radio to a specific frequency. We are tuned to a particular range of waves. Interestingly, different animals are tuned to different parts of the spectrum. For instance, bees can see ultraviolet light, which is invisible to us, revealing patterns on flowers that guide them to nectar. To bees, a poppy flower appears differently than it does to us. Snakes, on the other hand, can perceive infrared light, aiding them in locating warm-blooded prey in the dark. Mosquitoes also sense heat and carbon dioxide to find their targets. Sharks have a specialized system called Lorenzini's ampullae for detecting electrical signals, which helps them hunt in murky waters. Bats use echolocation, emitting and reflecting ultraviolet signals to navigate their environment. This principle extends beyond vision to sound and smell. What we perceive as melody or the scent of roses is actually just air vibrations and molecules. Our brains interpret this raw data into a rich tapestry of sensations. Consider you and a friend observing the same object. Are you sure you both see it in the same way? It turns out our perceptions can differ significantly. Take the case of Hannah Bosley, an individual with a unique condition called synesthesia. When she sees letters, she perceives them in color. J is always purple and T is red. To her, every word is a colorful spectrum. Hannah doesn't invent these colors. She genuinely sees them, and they remain consistent. Synesthesia blends different sensory experiences, and about 3% of people have some form of it. This means that out of every 100 people you meet, 3 might experience the world in a way vastly different from your own. Neuroscientist Vilayana Ramachandran, in his book, The Telltale Brain, explains synesthesia as a merging of sensory perceptions. For example, the texture of sandpaper might evoke an F-sharp note, the taste of chicken could create a tingling in the fingertips, and a symphony might be perceived in blue and gold. Synesthetes often find it surprising that others do not share their sensory experiences. Common forms of synesthesia include colored letters and numbers, taste-based associations with words, and color-based hearing. Some synesthetes experience number sequences as 3-dimensional shapes, while others perceive gender and personalities in ordinary letters and numbers. Synesthetic perceptions are automatic and consistent, not under voluntary control. If you have a similar experience, feel free to share it in the comments. I'm sure many people, including myself, would be fascinated to read about it. Interestingly, it's possible that Isaac Newton had some form of synesthesia. He invented a musical toy that displayed different colors on a screen for various notes, creating a visual spectacle to accompany each song. This device might have been inspired by sound-color synesthesia, where sounds evoke colors. Newton's unique sensory experiences could have influenced his development of the wave theory of color. Why do some people see the world in this way? Synesthesia is the result of talking to interference between sensory areas of the brain. Think of them as neighboring countries on a brain map that have transparent borders. Microscopic changes in the brain's wiring pattern can be the cause of different realities. The very existence of synesthesia shows that more than one kind of brain and more than one kind of mind is possible. Every morning, a small miracle happens. Your consciousness awakens, and you become aware of your surroundings, thoughts, and feelings. But this is only the surface of what is happening. There are billions of processes unfolding in your brain at every moment. Whether you're recognizing a friend's face, driving a car, or deciding what to eat for lunch, your brain is continuously performing complex calculations, all without your conscious input. Think about an action as simple as picking up a cup of coffee. Although this action seems simple, it involves an incredibly complex process. When a person picks up a cup, their brain performs trillions of calculations. First, the eyes scan the surrounding space to find the cup. Then, different parts of the brain coordinate the muscles in the hand to accurately grasp the cup. At the same time, the brain processes information about the weight, temperature, and texture of the cup at lightning speed, so that it doesn't fall and the coffee doesn't spill. What's really amazing is that the person is not conscious of all these complex processes. He just picks up the cup. His mind may be preoccupied with other thoughts or conversations. At the age of 19, Ian Waterman survived a severe illness that damaged his nerves, depriving him of proprioception, the ability to sense the position of body parts without visualization. Most of us can tell if our hands are up or down, even by closing our eyes, but Ian was deprived of this internal feedback. Doctors initially predicted that Ian would be confined to a wheelchair for life, but he decided to fight through the challenges. Now every movement requires tremendous concentration. To walk, he must constantly monitor the position of his legs, and to keep his balance, he must frequently monitor the position of his arms. Deprived of the ability to feel his feet touching the ground, he must carefully calculate each step. Yin's experience emphasizes the complexity of even the simplest movements. Our brains make trillions of calculations so that we can walk and think at the same time. No computer, no matter how advanced, can match the efficiency of this process. In front of you is 10-year-old Austin Neighbor. He's the world champion of child cap stacking. This is the rapid assembly and disassembly of pyramids from special cups. Austin can assemble a pyramid in just 5 seconds, while it takes the average person about 40 seconds. To understand how Austin's brain copes with this task, scientists conducted an experiment comparing his brain activity with that of a normal adult during the competition. The results were surprising. Austin's brain showed calm alpha rhythms, characteristic of a relaxed state, while the adult brain showed high beta activity, indicative of intense cognitive effort. This difference is explained by the neural connections Austin's brain has developed over years of training. His skill is ingrained in the physical structure of his brain, allowing him to perform the task automatically. In contrast, an adult faced with a new task must consciously think through each action, straining his brain to the limit. Interestingly, trying to consciously control a skill can often interfere with task completion. Take Dean Potter, the famous rock climber known for scaling sheer cliffs without a safety net. Through years of practice, Dean's brain developed specialized neural connections for rock climbing. He trusted his subconscious mind completely, performing the movements automatically without thinking. This effortless state is known as the flow state. Sometimes the unconscious is necessary because it processes information faster than conscious thought. For example, in baseball, a player must react to a flying ball in just 0.4 seconds, too fast to make deliberate decisions. Therefore, the reaction is automatic. Our brains continually make decisions below our conscious awareness. Richard Thaler and Cass Sumstein explore this in their book Nudge, describing how subtle environmental changes influence our behavior. For example, placing fruit at eye level in a store increases the likelihood of purchase, and an image of a fly in a urinal makes men more careful. Additionally, studies on attractiveness reveal that men find women with dilated pupils more attractive, even though they don't consciously notice this. Another study found that strippers' earnings vary with their menstrual cycle, showing they received twice as many tips during ovulation compared to menstruation. These kinds of experiments allow us to learn something important about how the brain works. The task of this organ is to gather information about the world around us and direct our behavior accordingly. And it doesn't matter whether consciousness is involved in this process. We are not involved most of the time, and we are unaware of most of the decisions that are made on our behalf. So why do we need consciousness? Why aren't we simply automatons following a preset program? Imagine you're strolling down a familiar street, lost in thought, when you suddenly notice a chair moving on its own. Instantly, your attention is captured. This is when your consciousness kicks in. Consciousness is essential for reacting to unexpected or unusual situations. When everything goes as planned, our brains operate on autopilot. Consciousness also plays a crucial role in resolving internal conflicts. For instance, if you're tempted to eat a burger but recognize that it's unhealthy, your conscious mind helps you weigh the decision. You can think of consciousness as the CEO of a large company. It doesn't handle every minor detail, but is responsible for shaping the overall strategy and making key decisions. As far as the brain is concerned, consciousness is a way for billions of neurons to see themselves as a whole, a way for a complex system to look at itself in the mirror. Take a look at this image. You've probably seen it before and know that it can be interpreted as either a young woman or an old woman. Every time you switch between these two perceptions, your brain undergoes changes. If you were to connect your brain to a special device during these switches, you might hear your neurons producing different sounds. For instance, when you see the young woman, your brain might emit a quick, while the old woman might produce a slower. These sounds reflect how your brain processes and chooses which interpretation to prioritize. Although the image itself remains the same, your brain is actively selecting which version to perceive. This process is analogous to decision-making in everyday life. As you watch this video, you might find yourself debating whether to like and subscribe to the channel or to abstain. On the surface, it seems like a simple choice, but your brain is engaged in a complex decision-making process. Billions of neurons form two competing factions. One group might be urging you to like the video, appreciating the interesting topic and presentation, reminiscent of Alfred Jarbus's experiments and Mike May's story. Meanwhile, another group of neurons might criticize the video for lacking depth, missing important aspects like synesthesia, phantom limbs, or why you can't sneeze with your eyes open. These neural groups compete to influence your decision, and the outcome is determined by which faction prevails. This decision-making process is ongoing. Even after you choose to subscribe, a new conflict might arise should you press the notification bell or not. Sometimes, we are aware of these internal conflicts. For example, try naming the color of the letters used to spell color names. For instance, if the word yellow is written in green, you should say green. This task can be challenging because one part of your brain wants to read the word, while another part focuses on naming the color. It's even more intriguing to observe how the brain functions in individuals who have undergone surgery to separate the brain's hemispheres. They may experience alien hand syndrome, where their hands act independently. For example, if you're cold and need to button your jacket, both hands would normally work together. However, with disconnected hemispheres, one hand might zip up while the other unzips. You can learn more about this phenomenon in the video, Two Consciousnesses in Your Head. All of this illustrates the complexity of our brains. Every decision and action results from numerous battles occurring within your mind. You are not a single voice but a chorus of different eyes constantly negotiating and reaching agreements. The human body operates like a symphony, comprising about 37 trillion cells working in harmony. However, we are constrained by our senses and physical form. According to David Eagleman, we are now at a pivotal moment where the fusion of biology and technology can help us transcend these limitations. By redefining what it means to be human, we can expand our perception of reality. Over the past 100,000 years, humanity has evolved from primitive hunter-gatherers to a technologically sophisticated civilization. Today, we hold devices in our hands that contain vast oceans of knowledge. We soar above the clouds like the gods of ancient times, admiring our blue planet from cosmic heights. Our thoughts race across continents in an instant, and our messages travel through the depths of space to reach distant stars. Even amidst the chaos of daily life, we outpace the fastest creatures on Earth in our iron chariots. All these marvels are products of our brains. What mysteries lie within its folds? If we can unravel these enigmas, what new horizons will unfold before us? Humans are increasingly learning to integrate various technologies into their bodies. You may not realize it, but hundreds of thousands of people already utilize artificial hearing and vision. So how do these technologies work? For hearing, there is the cochlear implant, which converts sound into digital code and sends it directly to the auditory nerve. The artificial eye operates similarly. A camera captures an image, translates it into signals, and transmits those signals to the optic nerve. Initially, scientists were skeptical. Could a meaningful dialogue occur between metal electrodes and living cells? Would our brains be able to comprehend these artificial signals, or would they become confused? It turns out that the brain is remarkably adept at decoding. It learns to interpret new signals much like we learn a foreign language. At first, everything may seem incomprehensible, but gradually, the brain discovers meaning and patterns. This is how Michael Chorost, a recipient of a hearing implant, described his experience. When the device was turned on a month after surgery, the first sentence I heard sounded like, which gradually turned into, "What did you have for breakfast?" After a few months of training, I could use the phone again and even talk in noisy bars and caves. Our brains are so adaptable that they can learn to interpret entirely new types of signals. What new senses might this allow us to develop? We are born with a set of senses: sight, hearing, touch, smell, and taste. We also have a sense of balance and the ability to feel heat and vibrations. But what if this is just a fraction of what we can potentially sense? Traditional neurobiology often views our senses as fixed and unchanging. However, David Eagleman suggests that our senses can be thought of as devices that can be plugged in or unplugged. The intriguing part is that our brain doesn't care where information originates from. It simply processes whatever data it receives and tries to make sense of it, much like a computer handling any type of input. Nature provides numerous examples of how different animals perceive the world in unique ways. For instance, snakes sense heat, some fish detect electric fields, and cows and birds navigate using the Earth's magnetic field. Hummingbirds and bees see ultraviolet light. Elephants can hear sounds over great distances, and dogs experience a world rich in scents. Perhaps in the future, humans might also develop the ability to sense magnetic fields or see infrared light. There are no inherent physical barriers to these possibilities. Our brains are prepared for such adaptations. I decided to look up examples of people with extraordinary abilities, and the list is astounding. Stephen Wiltshire, an artist with a photographic memory, can paint intricate landscapes after just a brief glance. Daniel Tammet, a synesthete and autistic individual, can perform complex mathematical calculations mentally and learn new languages within days. Conchetta Antico, known as the woman with supervision, has a fourth type of cone in her retina, allowing her to see about 100 times more shades of color than most people. Derek Paravicini, a blind autistic pianist with perfect pitch, can play any tune after hearing it only once. Shakuntala Devi, known as the human computer, set a world record by multiplying two 13-digit numbers in just 28 seconds. Ben Underwood, who lost his sight, developed the ability to use echolocation similar to that of bats. And there are many more fascinating cases like these. I'd like to emphasize that there's probably nothing special about the senses we're used to. They are simply inherited by us from a complex history of evolutionary constraints. We don't have to hold on to them. In 1969, Paul Bach-e-Rita conducted a groundbreaking experiment where he placed blind individuals in a special chair equipped with a camera that transmitted images to their backs through small pistons. Remarkably, the participants learned to see with their backs, recognizing objects and even perceiving their approach. This discovery led to the development of an entire field of research. For instance, the BrainPort device allows blind individuals to see using their tongue. A camera in the glasses converts images into light electrical impulses that are transmitted to the tongue, and the brain learns to interpret these signals as visual information. This technology has proven effective. For example, blind climber Eric Weihenmayer uses it to identify footholds while climbing. Notably, Eric is also known as the first blind person to reach the summit of Everest. It might seem unusual to see with your tongue or hear with your skin, but the key point is the incredible adaptability of our brain. It doesn't matter where the information originates from. What matters is that it is received. Another innovative device developed by Eagleman's lab is called VEST, which aids deaf individuals in hearing. This device, worn under clothing, uses tiny vibration motors to convert data streams into dynamic vibration patterns on the body. Remarkably, after just a few days of use, people who were born deaf can start distinguishing words. But the potential of VEST extends beyond assisting the deaf. Imagine being able to feel information from the internet directly through your body. You could sense air pollution levels, solar activity, or stock market fluctuations without checking your smartphone. Additionally, you could feel data from health sensors directly through your body, such as blood glucose levels, the ideal time to take medication, or even your concentration levels. At present, we don't know the limits, if any, on the data that the brain can perceive. But it is already clear that we are no longer children of nature who must wait for the slow course of evolution for sensory adaptation. We will invent for ourselves more and more sensory portals into the world around us. we will immerse ourselves in an expanded sensory reality. Jane Schuerman suffered from a rare genetic condition that left her unable to move, although she could feel her body. But scientists found a way to help her. They implanted electrodes in the motor cortex area of her brain and connected them to a computer that controlled a robotic arm. Amazingly, Jane was able to control this artificial arm with her mind as if it were her own limb. Jane addressed the arm. Go up. Now down, lower. To the right. Take it. Let go. And the hand obeyed the instructions. This experiment once again proves the plasticity of our brain. Not only is it capable of controlling our biological bodies, but also artificial systems. There's no reason why our brains can't do work on the other side of the planet or explore the moon caves while we eat our own rolls at home. Our species is on the cusp of something new, and we don't fully realize what it is. We are living at an unprecedented moment in human history, when brain science is merging with technology. What happens at this crossroads should change us. David Eagleman ends the book with the following words, and I agree with them 200%. What we become is up to us. Thank you for watching, and as always, a special thanks to the sponsors. What do you think about the topic of the video? Write in the comments.